everybody. I'm Jennifer Cunningham from the Office of Alumni Relations. And our Mountain Talk today is with a 3-time Lehigh alum. I'll tell you a little bit more about that in a second. Before I introduce our speaker, I just want to go over a couple of housekeeping things. We have 30 minutes today. Dr. Daly is going to speak for about 10 or 12 minutes, and then we'll open it up to your questions. You will ask your questions by putting them in the chat box at the bottom of your screen, and I will read those questions aloud so that Dr. Daly can focus on her answers. And we'll try to get through as many of those as we can. And this webinar is being recorded, so just keep that in mind. I think I have to say that for legal reasons as well. Dr. Hannah Daly is a assistant professor of mechanical engineering and mechanics in the P.C. Rawson College of Engineering and Applied Science. I think this is a fascinating webinar because we've all seen those poor kids walking around campus with broken legs, and we all think, how are they doing this? Well, Dr. Daly is trying to make that healing process faster by using mechanical engineering simulation techniques to measure bone healing. She's also the co-founder of a startup, and she has her very first in-person class tonight. Classes started yesterday for the students, so we really appreciate you being here on such a stressful or exciting day. And then I also just wanted to mention, so Hannah's class of 02, graduate degree in 06, and PhD in 08, was inspired to come to Lehigh by her grandfather, who is an alum, and she met her husband here, hoping the kids will come here, has tons of Lehigh connections. She is brown and white through and through. I'm very happy to turn it over to Dr. Hannah Daly.
Thank you so much, Jennifer. And thank you everyone for taking the time to be here today. I know we all have so many competing demands on our time. I am really looking forward to hearing your questions and having some conversation at the end of this short presentation that I have. Maybe the ideas that I'm going to present today are going to be new ways of thinking about things that you thought you understood, because bone fractures are such a part of our everyday experience. We all know somebody who's had a broken bone. But in my research here at Lehigh, we're trying to take a really unique engineering-informed perspective on understanding this process of how a bone heals. So just a little bit about myself. As Jennifer mentioned, I have deep Lehigh connections. All of my degrees are in mechanical engineering from Lehigh. I had bouts of leaving the university and coming back, almost as if it has this inevitable gravitational attraction to bring me back here. But I truly believe Lehigh is one of the most special places in the world. I tell prospective students this, like, I can't totally describe it for you until you get here. You're just gonna know. After I finished my PhD from Lehigh, I had a really crazy and unexpected opportunity to go to work for a medical device incubator in Ireland. And living overseas was something I kind of always wanted to do, but I didn't have a plan for how to make that happen. My husband and I were both looking for postdoctoral research positions, and we had this chance to go to someplace totally new and try something out. And this was my first opportunity of working in the orthopedic industry, and that was a real turning point in my career. I'm guessing a lot of you have had similar experiences where you have some educational background. For me, that was mechanical engineering, but then doors open along the way of your career path that kind of take you into a direction where you might draw on the things that you learn in school, but you're applying them in a totally unexpected way. And I think that's really the power of education. This is what I try to tell my students when I'm advising them. You know, my undergraduate students are so stressed about needing a life plan. They're like, look, you cannot predict what is coming for you. And so you just need to be open-minded. So I got this chance to work at a medical device incubator, and I developed a technology for an implant to help improve bone fracture healing. And after a couple of years of working on that, discovered that there was a really strong possibility of having a measurable clinical benefit. It just means the patients would probably do better with this technology compared to the current standard of care. So I got an unexpected chance to become an entrepreneur. So I co-founded a company called OrthoExcel, which is based in Ireland because that's where we started this project. And I still serve as the chief scientific officer of that company. And so we design and manufacture trauma implants that all kind of are built around the central idea of improving bone fracture fixation by changing the mechanical environment. And for any engineers in the room, you know, you might recognize that there are mechanical principles at play that kind of crop up in unexpected ways. I'm going to describe a little bit about that through the research story that I'm going to tell you, but today I'm going to focus on what we do in my lab here at Lehigh. And what I love the most about what we do is having really close partnerships with orthopedic surgeons. So we take a lot of medical imaging data. You may have heard of CT scans, CAT scans, or like three-dimensional X-ray pictures. So we use those to do mechanical simulations to try to understand what's going on with bone fractures, fixing them using surgical implants, and getting them to heal. And that's what I'm going to talk about in this like couple of minutes that we have here together. So I just want to give a little content warning in case anybody does not like seeing gory pictures. You might want to just look away for about 15 seconds. I'm going to reveal what's behind these images here. 3, 2, 1. Here we have a couple of shin bone fractures. So we got Tennessee Titans Mark Mariani, we got the Louisville Cardinals Kevin Ware, and the Boston Celtics Gordon Hayward. Gordon Hayward, if you look up this injury on YouTube, you can hear like a video recording where you can actually hear the sound of the bone popping. And I bring this up because these are really horrific looking accidents, right? But all three of these guys had the same surgical procedure and they all made a complete recovery and returned to sports. So it's the worst day of somebody's life when it happens. There's a really good shot at having a complete recovery. And what that complete recovery looks like is a period of typically 3, 4, 5, sometimes 6 months of gradual reconstitution of the structural integrity of the bone. So if you think like an engineer, those terms are going to make sense in the context of what we understand about buildings and cars and any other structure that needs to be able to hold itself together and bear weight. That's what the job of your skeletal system is. It needs to hold itself together and bear weight. And so here's a series of X-ray images that were taken about every 6 weeks over a timeline of healing for this guy. He's a 32-year-old guy who got kicked in the shin while playing sports. And you can see the fracture line is really clear and crisp. And then over a period of time, it sort of fills in with this brand new tissue. And we call that tissue callus, but it's not like the callus you would get on your hand from lifting weights. It's a brand new bone. So that brand new bone is there to hold everything together. And now, if you're a surgeon, the typical way that you would assess bone healing would be to look at these images and might compare last time and this time and try to see, do we detect an improvement by just the visual appearance of this fracture on the X-ray? But it can be really hard to find more subtle differences. Or in the case of a patient who's not healing well, how do we know really early on in that healing timeline that something is not going right? And what I do at Lehigh is an application of engineering mechanics that allows us to measure something in a human being using a non-invasive technique that we have no other way of measuring in a clinical setting. And I think that's just so amazingly cool because, when I was a student studying engineering, I had no idea this was one of the things that you could do with it. So here's an example of a way that we would build a model to enable what we call virtual mechanical testing. So if anybody's ever been in an engineering lab or you've walked past a lab, you could picture somebody putting a sample for something on a big machine that would apply some kind of loading to it and measure what's happening. We cannot do that with a person. It would be unethical, and also nobody would want to participate in that kind of a research study. So we need to do it virtually in a simulation environment. So what we do is we take our CT scan, that CAT scan, which is again, like imagine it like a salami with lots of slices. So we reconstruct the salami in 3D, and we can identify the types of tissues that are there. So in this slide, the gold is the old bone. So this is the tibia or the shin bone. If you reach down to your own leg on the front side of your shin, that is the bone that's in gold here. And then the red part on this picture, that's the new bone that has formed for this patient because some amount of healing has taken place. And then to do this virtual mechanical testing, what we have to do is take this 3-dimensional model and we have to put it into the simulation environment. And this is called the finite element method. Some people are going to be familiar with that. Some people aren't. The way to think about this is just a way of simulating what would happen to the structure if we can put loads on it. And you can choose any kind of load that you want to. But we want to be able to understand the difference between really good hard bone, which would be like tan here for any mechies out there. That would be a bone that has a high elastic modulus or Young's modulus. And the brand new bone, which would have this kind of this blue region here, lower mechanical properties. It's softer, but it's still there to hold the bone fragments together. So we're going to put everything into this virtual simulation environment. And then I'm going to show you one little tiny story of something super cool that we can do with this virtual mechanical testing This is an example of a clinical research study, which means this is done on real patients who had real injuries. All of these patients have the same kind of fracture of their shin bone, and all of them have the same kind of treatment, so same surgery. And then what we did at 12 weeks, so 3 months after their injury, we took them for low-dose CT. So we got that scan, and then we put the model together to do virtual mechanical testing. And then using the results of that virtual mechanical testing, we can generate a percentage score that tells the surgeon how healed the bone is. So if you're used to looking at data, this is going to make a lot of sense. If this is unfamiliar, I'll just give you a little orientation here. So the gray box in the middle here, that represents the middle 50% score. So if we have a group of people, the middle 50% are going to have scores somewhere in the high 70s up to about 100% for their healing score. The way to think about that is that a score of 100% would mean that the bone is equal to its mechanical properties before it was injured. So we're looking to get people up to that 100% line. There's one little lonely red X floating down here. That's a patient with a problem. So this is a patient who had a delayed healing. And what we can see if we look at the three-dimensional model, you can kind of see daylight shining through the bone fragments. That is not a good thing, right? There are some reasons why this patient didn't heal well and some evidence that they weren't healing, including this broken screw here. So this happens all the time. If the implant is in the body for too long and doing the job of the bone for longer than it was designed to, you can get fractures of the metal hardware. So this is just like if you take a paper clip and you bend it till it breaks. Any piece of metal will do that. So it's nothing wrong with the screw itself. It just means that it was bearing load for longer than it was meant to. So we have this healing score, and we can use it to understand the expected outcome for most patients, and we can use it to identify patients who are really extraordinary. So now I'm going to show you a really cool way of differentiating between patients who are kind of on a good path and patients who are on a bad path. So again, this vertical axis here is that percentage score. We're looking to see people above the 100% line of mechanically equivalent intact bone, and 0% would mean no healing has happened. So if I break down a group of patients that we studied into two sort of subgroups, one subgroup would be normal patients. And this just means that they don't have anything in their medical history that would indicate a kind of pervasive biological problem. And the other group would be patients with comorbidities. And this is something we're all very familiar with in the post-COVID world. Comorbidities are baseline health conditions that can increase your risks of more bad things happening if you have some other kind of injury or illness that's added on top of that. So for bone healing, comorbidities that we know can be problematic would be things like smoking and vaping, diabetes, systemic diseases like HIV and hepatitis C, alcoholism or substance abuse, ischemic heart disease. There's a whole laundry list of things. Basically, anything that's going to choke off the blood supply to the tissues is going to put a patient at more risk for something really bad happening with their bone healing. But typically in a clinical trial, we would need thousands of patients to be able to see these effects because they're not real dramatic effects. And so you need very large numbers to study it. Now I'm going to show you the results of doing this virtual mechanical test, our engineering simulation technique. So the first thing to look at is this normal group of patients. So these patients are, kind of at or above the 100% line. We picked only a subgroup of patients who have like sort of simple fractures, nothing real nasty like the pictures that I showed you guys at the beginning of this talk, no open injuries with the bone sticking out. So they're, kind of on track in the normal group. Now, if we look at this comorbidities group, the patients with smoking, diabetes, HIV, et cetera, we see that the box here, this blue box, is hanging out below that mechanically equivalent 100% line. This difference between the two groups is actually 23%. And in the world of medicine, a 23% difference between patient groups is an enormous difference. Like, doesn't seem like that big of a deal in our everyday way of thinking, but this is a huge difference. And this is a kind of subtle thing that's really hard to see if what you're looking at is a picture of an X-ray. But because we have this virtual mechanical test where we can non-invasively get in there and measure how much healing has taken place, we can show that these patients are on a slower timeline of healing. And we would be able to pick out, like I showed you in the previous slide, a patient who was really falling out the bottom of their healing curve and not getting where they needed to be. So the overall objective here with this research is to be able to help surgeons differentiate between, for example, two fractures like this. So these are two real patients that we studied in clinical studies that gave the data for what I'm showing you here. The patient on the left had no risk factors, and the patient on the right here, this is the shin bone of a person who had a very similar kind of injury. So these are two different people, very similar injuries, but the one on the right is a smoker and the one on the left had no risk factors. So using these techniques, we can reach into the data and find things that a surgeon can't detect by just looking at an X-ray. And this is powerful because I'm really excited to develop these techniques as a diagnostic tool. Like if you go for a CT scan, I would like a surgeon to be able to order a diagnostic test, like ordering a blood test, except that the results of that diagnostic test would be the virtual mechanical test score, so a percentage score for healing. It also can change the paradigm of the way that we think about designing clinical research studies, because instead of needing thousands of patients to detect differences, we can use much smaller numbers of patients to do that. So it makes clinical research a lot less expensive. And it also makes innovation a lot easier to achieve, because if you have a new technology, and I guess I'm speaking with a little bias because I'm kind of an entrepreneur in this industry, if you have a new technology and you want to test whether or not it works, it's very obstructive to need to run a clinical trial with thousands of participants. But if you can do it with much smaller numbers, it opens up the innovation ecosystem for smaller and medium-sized enterprises to be able to do new and creative things in this orthopedic implant space. So I'm gonna close my talking time here with just a couple of examples of pictures of cool research studies that my group has done. We don't do just bones of the lower leg. We look at a lot of different things, but all of it is related by the ideas of using medical imaging, using mechanical engineering simulation techniques, and closely partnering with orthopedic surgeons to design studies that are going to help them answer questions that they couldn't answer any other way. And for me, that's really inspiring. That's why I get up every day and continue to do this, because I find it just so cool to think that we as engineers can contribute to enhancing life, freedom, mobility, and recovery after traumatic injury for patients who really need it. I think with that, I'll stop. And Jennifer, if you've got any questions in the chat, I would be very happy to take them.
Nice. Okay, that's your cue, everybody, to write your questions for Dr. Daly. While you are thinking about those, quick question, have you ever had a broken bone yourself?
Yes, I have had a broken bone, but it's the most pathetic one that you can break. So I broke the tiniest bone in my foot. It's called a sesamoid bone. It's the size of a pine nut and it sits underneath the big toe. Very common injury in dancers. And basically I was hiking in bad boots and I impacted down on the bottom of my foot and cracked my sesamoid. I was in like a sad little orthopedic shoe for 3 or 4 weeks, something like that. But that happened to me way back before I knew anything about bone healing. I had no dreams or aspirations at that time of getting into the orthopedic industry. So I was just like any other patient coming in, but I've had 2 fractures of bones in my kids. And so, I go into the orthopedic surgeon's office and they're like, oh, are you a nurse? You know things about this? I'm like, no, I do know things about this. So let's have a conversation.
Nice. All right, we have a question from Colin who asks, are in silico trials currently being used for medical devices?
Colin, I love that question. Okay, so no, but this is absolutely where we want to get.
But wait, can you first describe what in silico trials are?
Absolutely. Okay, so in silico just means we do it in a computer. So this is again under the category of virtual things, not real experiments, but virtual simulated ones. So something that we do in my research group that I didn't talk about a lot is develop numerical algorithms that can predict the process of bone healing. And actually the second image from the left here kind of shows the results of one of those simulations. So this is a virtual model. There's no animal or human data involved in this, but we have an algorithm that can show where bone would try to grow based on the mechanical conditions that are involved in this fracture, which was held together with a plate and screws. So definitely the exciting research horizon in this space would be the idea of having reliable algorithms that are validated in vivo data. So that just means we can prove that our simulation gets the same result as we would expect to see in an animal or in a human. And then use that to build out a much larger parameter space, if you will, explore things that you would never try if you were just, designing an experiment with limited financial resources to do in an animal or in a human. So instead of, studying 10 sheep or 50 humans, we could study thousands of different cases and combine them all together and then make considered decisions about selecting what kinds of implants to advance the clinical trial stage with, putting them in a person, or perhaps study the impact of very extraordinary circumstances where patients, for example, might have multiple biological comorbidities or sources of compromise with their health that would put them at a kind of very low fracture healing response, and then see what happens to them. Those patients would be very rare to find out if you were doing a regular trial. But now the idea of an in silico trial is that you could combine together all of these factors. So yeah, Colin, very, very forward-looking visionary question there. I would love to be doing that in 5-10 years.
Great. I had the same question here as Terrell. Dr. Daly, has your research suggested innovative approaches to orthopedic surgeons to use in helping bones heal more rapidly?
Yeah, okay, so Terrell, that's a great question. This is the dream, right? We want to be able to take what we do in computer simulations and in these modeling environments and see that translated. So in the research parlance, we would call that translational research. Take something that you discovered from basic science and use that to change clinical care in some way. So in part of my career, I've been able to do that. The part that I didn't really talk about today with my entrepreneurship experience, we did research on what would be the kind of ideal design of an implant to get the fastest possible fracture healing result. And then I have had the extraordinary good fortune to be able to carry that idea all along the translational pipeline, from a concept sketched on a whiteboard to a design, to bench testing, to cadaver studies where you test things out in parts that you harvest from donor bodies, to putting it into a large animal model, to seeing it used in humans, and then actually to bring that full circle and show a benefit with the technology. So we've my invention or co-invention of an orthopedic implant, we're about to publish data showing that it actually benefits the healing process. So yeah, like that's definitely the dream. There are other things that I'm working on right now that I'm really excited to see how they can change orthopedic practice, because orthopedic surgeons understand a lot about mechanics, but without numbers to attach to it, because you can't go in there with a little microscope or a little strain gauge and measure what's really happening. Like in the yellow hot region here in the fracture, we had a femur, a thigh bone, and that yellow orange stuff describes kind of the mechanical environment, right? So the hotter the color, the more mechanical stimulation or strain in this case there is for any mechanical or civil engineer. So there's a lot of debate right now about what's the right kind of mechanical environment for fracture healing, and a lot of misconceptions that surgeons have. And so one of the areas where I'm looking to innovate would be to bring tools like this that you see on the screen here into the hands of surgeons so that they can understand not just qualitatively, more or less of a certain thing, but actually to put some numbers around it and use that as design guidance for future implants. So yeah, definitely, like there's going to be an increasingly close relationship between orthopedic clinicians and engineers working to bring those knowledge bases together to improve human health, for sure.
Right. Sort of related question from Chuck. It seems the modeling depends very heavily on the mechanical properties you apply to the regions defined in segmentation. So how accurately can you define the materials or properties during that segmentation?
Chuck, I love the question. You guys are so on point with the questions.
Right?
Like you're all already experts. Okay, so this is an awesome question. So mechanical properties of bone are very well understood, because you can get a bone out of a sheep or out of a cow or out of a person who's deceased and donates their body to scientific research, and you can do mechanical tests and you can measure the properties. But the new bone that forms while a fracture is healing, that is not something that you can measure in a human, because when people typically donate their body to science after they've died, they haven't had a fracture 10 weeks ago we can study. So the closest model that we have for understanding the mechanical properties of that new bone tissue is from a large animal, a sheep. And there are biological reasons why we study sheep instead of other types of animals, but basically their bone metabolism, the way that they heal and the timeline that they heal is a good it's a good surrogate for humans. So I have a research partnership with the Musculoskeletal Research Unit at the University of Zurich. Actually, one of my former PhD students, Peter Schwarzenberg, had an NSF Institute for International Education Graduate International Research Experience Fellowship, which is a real mouthful to say, but he got to go to Zurich for 6 months to engage in this collaborative research. And what we did was take mechanical testing data from animals, from these sheep, who had had a fracture and it was fixed and they had healed partially. And we used our engineering simulation techniques with a large scale computer optimization to kind of match up the mechanical properties that we were assigning in the model based on what the image shows to the mechanical testing data. So using this validation approach, we have this really good model now for what we think the mechanical properties are of this new bone that forms. But you're absolutely right that understanding those mechanical properties is the key to kind of cracking this whole thing. Because if you're using the wrong material properties model, then you can get conclusions that are a little bit off from what you think you were expecting.
Great. Okay, we have a comment here from Carolyn who says she's a former Lehigh mechanical engineering grad who jumped into the orthopedic trauma industry after graduating. This is fascinating. She's been out of it for 15 years, but it's phenomenal to see the testing option moving away from animal trials and into computer simulations. Good job. So
thank you so much.
Yeah.
Just the explosion in computing power has really enabled some things. I'll regale my PhD students with stories of what I was doing back in the dark ages of computer simulation. So I was using the same kinds of analytical approaches, but just at like a tiny small scale compared to what we can do now. At Lehigh, you may not know about this, but we have these phenomenal high performance computing or HPC resources that are partly supported by the university, partly by funding from the National Science Foundation and other sources. So this makes this incredible computer infrastructure that we have here for research at Lehigh, where we can throw like thousands of simulations onto this computing cluster and get back answers. Like, what my students can do in a week now would have taken me a year. I don't even know. Nice. Back when I was a student. So it's really that explosion in computing power is really the credit for what we can achieve now and what we can dream of doing that we had no ability to conceive of before.
Well, Carolyn, next time you come to campus, I suggest that you call up Dr. Daly and go have a coffee or a beverage, because I bet you'd be blown away.
That would be awesome. Please do. Yeah. And the invitation stands for anybody, like alumni, when you're back on campus, if you're interested and you want to swing by and just have a chat, we're here, doors are open.
Yeah, excellent. All right, so we have 2 minutes left. So if you can answer Daniel's question in 1 minute, and then I'll close it out by just talking a little bit about the Soaring Together 50 years of coeducation. So Daniel's question, is CT the only imaging modality that can be used with these bone healing models?
Super question. Okay, so CT is preferable because the X-ray attenuation is what you measure. Since it's a very important question, I'll give you an informed answer. X-ray attenuation or Hounsfield unit correlates linearly with mechanical properties. So CT is preferable if you're studying bone. If you're studying soft tissue like tendons, ligaments, muscles, then you got to switch over to MR. So what we do is all CT based because that's ideal for bone.
Fantastic. That was quick. All right, so thank you everybody for coming. We have 1 minute, so I did just want to say that this is part of our Soaring Together celebration. We are highlighting over the next year, really over the next 4 years, the fact that Lehigh's undergraduate class of women was admitted 50 years ago. On Saturday, we had a fantastic first-year rally out on the UC lawn. And we had our first woman, Karen Stuckey, who did the flag adoption ceremony. And so Dr. Daly is just another great example of why it was a smart idea to allow women in. And you see she's collaborating with a lot of men. So it's not just about celebrating the women that came here too, it's about now the co-education, and we're stronger together. So thank you so much, Dr. Daly. Your grandfather would be proud. And I'm glad that everyone showed up. And if anyone has any other questions, you can email us here and we can get those questions to Dr. Daly. And good luck.
I'm also on Twitter. So if anybody wants to reach out to me directly, you can DM me on Twitter. I'm at Daily Ortholab, or just snap the QR code there.
Fantastic. Fantastic. Good luck with your class tonight. And thank you.
Thank you very much. I'm excited to be back in a classroom.
Yay. All right. Bye-bye, everyone.